Hi everybody. So we're in the next video. So we were wondering how to tackle this complex problem. How to understand. And this is simply done by considering a control volume. So we just design our control volume when we want to have it. Let's assume it here. Why not? Okay, now we have to do the zoom in to the control volume. When we have the volume, like this kind of shell surrounding the volume, we have the flux and the normal vector. So what are we trying to study? We can actually study any kind of variable that is associated with the concentration per unit mass of a conserved scalar. So basically what I mean is that we can just, for example, consider some intrinsic properties of a given substance, like as you see here, a specific enthalpy, why not a specific entropy, specific internal energy. We can have the concentration of CO2 per unit mass as well, momentum per unit mass as well. So this phi actually is any kind of variable that is a conserved scalar. And we will start then, we will focus in this course on the temperature equation. Therefore, a good idea is to study from the beginning either internal energy or enthalpy, specific internal energy or a specific enthalpy. Okay, now let's go and do some math. So let's go to the blackboard, the virtual blackboard. Okay, so the first thing is to just draw just the control volume as before. So this is, imagine you have a potato, and to make it three-dimensional we will do like this, and we have a quantity enclosed in there, and this quantity enclosed, let's call it enthalpy. So this is the quantity we're interested in, enthalpy. So if you look at this figure, you can actually see, well, the enthalpy is just the specific enthalpy integrated by the volume. Okay, and this is over the volume. So normally in the class I will ask if this is correct or not. So just you think 2 seconds from in your seats and you think, what is the wrong thing here? So the wrong thing here is that I just forgot to put the density. Okay, so in order to have a list to be consistent with the units, a list. So now we have here everything is fine. Okay, now we know that we have enthalpy enclosed within a volume V, and it can stay like that forever. So if it stays like that forever, it means that dH dt is going to be 0. So there is no change of enthalpy within the volume. Okay, but this is boring. So let's put some flux. Okay, so we will put, like, we have a flux of enthalpy that comes in and a flux of enthalpy that go out. Okay, so if there is a change of enthalpy, it's because there is a flux. But now let's draw this. So we will have, first of all, we have to design the like a normal vector. And then we will put the given flux. So let's put it like this, given flux, small a, and over a given surface. Okay. Now, based on that, on those variables that we just defined, then we will just express f in and f out. So this is going to be equal to two integrals, and we will have here f in, f out, and then over the surface. Okay, so this is the shell, so the over the surface. Okay, this looks correct, isn't it? What is wrong with this? There might be something wrong. So just try to think from your seats again what is missing. Something that is fundamental is that I will just scratch down later. So this is actually incorrect. Let's put it like this. What I want to say is that we need to have into account the normal vector, so the dot product of f with respect to n. Imagine you have the flux, and the flux is actually tangential to the shell of this control volume. So strictly speaking, you don't have any flux. So because the nothing is going to be coming out from the domain. So the net flux, so the actual flux you will have, is the projection of f with respect to the normal vector. Okay, so in that sense, I will add this again here, f in ds minus, screwed up, just be patient with me, and so f out. So is this correct now that we have the normal vector? No, this is almost correct. There is a problem with the sign only. Why? Because the actual sign that we want to take into account is, I will tell you, this. So there is a sign mistake. What is the sign mistake? The sign mistake is in here. Why? You have to take into account the convention of the normal vector. Okay? So the normal vector is always pointing, in this case, outwards, which means that any flux that is coming inwards, when you multiply this or you project it with the normal vector, will give you a negative sign. So in order to have a positive flux, we need to put a minus. Okay? I hope that is going to become clear during the rest of the course, but I think it can be understood. Okay, so right now that we have everything, then we can just put, I will just write it in here. So the h dt, so d dt plus, and now we will have just, okay, I had missed this one before, so now we will have the complete flux, so I don't have any subscript, and this is dv, and this is the equation that we have now. Okay, now we have a temporal evolution, and we have a term that accounts for the flux that is coming in and is getting out. This equation can become even more interesting. How? If you have fluxes and now you have a evolution of this quantity, what else can actually give you a change in this quantity apart from the fluxes? Do you think, maybe you're already answering behind your screens, you say, okay, maybe I need a sink or a source to make things interesting. So we will just put, oh God, here, we'll just put a source, let's call it S, a volumetric source, okay, like this. This is V and this was also V in here. So, ladies and gentlemen, we have our integral equation describing the evolution of the quantity H within this control volume. Okay, now the idea is that we want to have all integrals to be volume integrals, which means that we want to change this somehow and to express this quantity within a volume integral. Any clue what we should do? Okay, maybe I think two of you already answered behind your screens that we have to apply the divergence theorem, which means that we will have something like this. And this is what was missing to have all terms in terms of volumetric integrals. So this is the last expression you just saw before. All terms are in terms of volume integrals, and we have the quantity phi here. So it's basically the scalar we want to conserve, and it was the one that we call H just before for enthalpy. This is just something more general. So here the density, which is the density of the carrier fluid, and also the quantity we're interested in, they depend on space and depend on time, as the same as the source. Okay. We also want to investigate now this flux. What is this flux about? Okay. But before learning or something about the fluxes, let's just obtain from the integral equations a differential equation. And this is right now possible because all integrals were expressed in terms of volume. So now we just factorize and we make a mental experiment in which you shrink this quantity as much as possible, so that at the end we consider just only one differential delta V. In that sense, in order this to be conserved, makes necessary that this quantity here is going to be 0. So for this mental experiment, when we shrink the control volume to a volumetric differential, we end up having this quantity being 0, and voila, we have obtained the partial differential equation for the description of conservation of a scalar phi. I have a source. Okay. The next step is to understand what is this flux about. And the main message in here is that the flux, it can be decomposed in two contributions, a convective one and a diffusive one. And the convective one is expressed by this. So you have a given velocity of the carrier fluid, the density of the carrier fluid, and then the scalar you are studying. Then you can imagine, for example, you have many particles. So you have particles of a given molecule, and here a different one. and then at different times you have these particles being transported with a velocity v, and this is what is we call the particles are being convected. So this is the convection, okay, and this is the mathematical representation of this flux. So this can be represented by, in this example, this is an example you will do this today, as you start today, this week, on the convection of a given perturbation. Imagine you have a perturbation, and this perturbation is going to be just convected by the carrier fluid. So how does it look like? You see that the initial perturbation in this kind of like two triangles, let's say triangular shape, is just convected. This is a periodic boundary condition, therefore it will show up in the left, okay? And what I want to say here is this perturbation doesn't change. The only thing that changes is that it just somehow shift in space, but the perturbation itself is the same, doesn't change, okay? So the shape is maintained. So this is a convection, pure convection. Let's go now to the second one, which is the diffusive flux. And a similar example, then you have two particles. You have a concentration of a quantity A and a quantity B, and you have a very steep gradient, or you can call it sharp gradient. You can think also in terms of temperature. You have a region of very low temperature and a region of very high temperature. What do you expect? You expect that this initial condition is not at all equilibrium. So you expect that the high concentration goes to a lower concentration, and the same from this side. So little by little, you will see that this in the example of the particles, they get mixed, and then at a certain time they will reach a steady condition when everything is in equilibrium. So what drives this diffusive flux? So as you can see here, the first condition is the gradient. So if I plot, let me just plot it in here. So you have the gradient, a steep gradient. So let's call it temperature. This is x. This is temperature. And then you have, let's call it, you have very high temperature, and suddenly you have a very small temperature. Okay, this is a rod, let's say. So this is the rod. So this is very high and very low temperature. So in this sense, you realize that you have a very steep gradient, and this is what actually drives the diffusion of flux. So you can say the flux of diffusion is proportional to the gradient, and that's all. When you don't have gradient, you don't have flux. Now there is something here that you can call it a constant, which is nothing that in this example can be, for example, the thermal diffusivity. So this is the proportionality constant that will somehow associate your flux with the gradient. And the last thing that is of importance is the sign, which is a minus in here, because it means that with this sign, this or let me put the steep, like something like this. So this is a negative slope, okay, but the flux is gonna be in the positive direction. So this is how, or what the science actually needs to do to put the right direction in the flux. So we go to the previous example. If you remember, in the previous example, the diffusion was going there was no diffusion, was a convection, and the perturbation were convected in this direction without changing in shape. Now in diffusion we have this kind of behavior. So you see that at the beginning it goes very fast because the gradient is fast, but as it evolves the gradient is getting smaller, so there is less diffusion, so less flux. So if you go actually into the analytical solution of such an equation, you realize that you have an exponential decay in the flux. So theoretically speaking, it will never end. Okay, of course in reality you have a certain period when you have a very fast flux, then a slow flux, and then you eventually reach a steady condition. And this is the equation we were maybe I haven't introduced right now, but this is the one I gave you in the previous example with the temperature. So here we just consider a multidimensional, in this case let's call it three-dimensional gradient operator with this nabla. We need a density of the carrier fluid, and also, as I told you before, the thermal diffusivity and the minus sign. So this is how the diffusive flux is expressed. Okay, so we have actually derived what we wanted, a unsteady convective diffusive reactive equation, and this is what I will write right now. So we will just play with the scalar phi. So the unsteady diffusive, I have here the velocity, no, sorry, convective, then diffusive in here, and then reactive. Let's put the source. So just to write it down so that you actually remember of the milestone we have accomplished today. So this is normally known as CDR, so the unsteady CDR equation. So this unsteady convective diffusive reactive equation is the general equation, and sometimes we don't need to solve the unsteady, we just need the steady part, or sometimes we want to have the diffusive part with that convective part, or the other way around. So it's a good idea to have in mind the mathematical structure that represents any of these equations when you have the unsteadiness, when you have the unsteady part, and so on. So in a rigorous way you can actually demonstrate the structure of the mathematical equation, the partial differential equation, based on these coefficients a, b, c, d, and so on. And you realize that given these coefficients you have three types of equations. You have elliptic, parabolic, or hyperbolic, and each of these equations is somehow treated in a different way, and this is what I want to show right now with the following example. So let's draw the example I'm interested in. So as you may know, some of you, so in the department we are very interested in combustion chambers of gas turbines, and I will just draw a very schematic combustion chamber. In here we have the flow going inside the midsection when you have a sealer, and maybe you have the injection here of fuel, and then you have the flame like this. And depending on the incoming reactants, then you have sometimes like hot spots created in the flame. Okay, and these hot spots, so let's put it a little bit larger, they are actually convected with the mean flow, and as they convect, they are getting smaller because they are diffusing as well. So these temperature pockets are being diffused, and this kind of phenomenon, with the tool we just created, the convective diffusive reactive equation, we're able already to describe it. And let me just write it down. So we have, let me write it in terms of H. So we have the unsteady term, then we have the convective term, then we have the diffusive term, and the source, which is actually creating the temperature that you can think is a sort of reaction. Okay, this equation is recognized to be a parabolic equation. Now imagine a situation when these pockets are being convected very fast, and for some reason, maybe the substance or the physics of the fluids involved in this problem, they are not being diffused much. So in that case, you can say I will have a problem which is also unsteady, which is convective. But we can say that this diffusive part, because the convective is very large in comparison to the diffusive part, and the diffusive term also is small because of some properties of the fluid, then we can say we will express this equation as this. So in the case when we actually ignore the diffusive part, this equation is going to be called hyperbolic. Okay, so now the question, just looking at this, I would ask, for example, which of these two equations do you think is more complex, or what is, let's say, harder for numerical discretization and to obtain a solution? So most of the time people think, of course, I mean, you have here a one more term involved here, this term here, we don't have this term, this equation is shorter, therefore this is going to be much simpler to solve. And this is actually not the case. You will realize that the diffusive term, what as I want to call it all the time, is our friend, because diffusive term allows to have smooth solutions, and smooth solutions are nice always for numerical discretization. So let's have an example in here. As you remember the previous little animation with a convective flux, imagine that you measure here in a point A and then in a point B, point A, point B, and under this equation you may consider that you have a pocket of temperature, let's call it temperature in here, this is X, which is very steep, also almost like a sort of this triangle example we just saw before. If we don't have any diffusion at all, we will expect that this is going to be convected and it will arrive at the point B like just being transported with the same shape, nothing changed. In this case, however, we will have maybe the same initial distribution of temperature. We have here point A, B, then we have here this peak, but as it evolves, it goes a little bit smoother, and maybe when you arrive at B, it's going to be something like this. So it gets smoother, it diffuses. Now, when you want to discretize this, imagine you have the X dimension and you discretize it in some cells. You will need to have a lot of cells in order to be able to resolve these steep gradients imposed by this distribution of temperature. However, in this case, you will have maybe, you will in regions with steep gradients, then you will have also the mesh. But in most of the domain, you will find that the solutions are smooth, you don't have steep gradients, and then you may have actually coarser meshes. Also, these hyperbolic equations, they allow for discontinuous solutions. So you may have also solutions when you have, imagine you have like a step like this, and this step will be maintained, so you will have a discontinuity that doesn't disappear, and this is very, very critical for assigning an adequate numerical discretization method. So if you use already a parabolic, if you consider a parabolic equation, these discontinuous solutions will not show up because of these smoothness properties of the diffusive term. Okay, so this is one part of the difference between a parabolic and a hyperbolic case for our transport equation. Another thing which is of high importance, high interest, is how you impose the boundary conditions. You will see here that the information in this problem, when described by this equation, the information flows in all directions. So you may have, you have convection that goes from left to the right, but you have also diffusion, and diffusion is happening in all directions in here. Okay, so it is diffusing in the west, south, north, east directions. So the information is flowing in all directions. So it means that we are allowed, or we have to impose boundary conditions everywhere, so that the problem is well defined and well posed. In a hyperbolic case, however, is a different thing. In this example of a hyperbolic equation, we may have just one direction in which the information is flowing. So in this case, we have just convection, so the information is flowing from the left to the right. That's all. So I put this example sometimes. Imagine you impose a boundary condition at the outlet. So in here, well, or in here, it depends what you call the outlet. So you impose a value, and if the information is only flowing from the left to the right, this information of the boundary never reaches the particles that are actually flowing towards the outlet. So this information is never reached because the information is only coming from the inlet to the outlet, from the left to right. So when this point arrives to the outlet, you will have a conflict because there are two conditions that need to be fulfilled at the same time, which is impossible. and the solution will crash. So this is already a condition or something that tells you what is to be done so that a problem is well posed in a hyperbolic problem. So in this case, we are not allowed to impose a boundary condition at the outlet. Otherwise, things are actually wrong and everything will crash. So this is so far for parabolic and hyperbolic cases. So we have already observed what is parabolic, what is hyperbolic. Now we will see what is elliptic. So in the elliptic equation, you will already forget about the unsteady term. So we have here t, and I will just give you an example. So we have, I will just write again so that you remember. Let's put here a source, and for the elliptic equation we just say we don't want to have the unsteady term, so it just vanishes. So it vanishes and we get the convection diffusion. And just to make a more illustrative purpose, we just also neglect the convective term and we end up with the so-called heat equation. Okay, and the heat equation is a elliptic problem. Which means that, or just so you remember, here the information also flows in all directions because of the diffusive term, and is unsteady. So it's steady, or it means it doesn't depend on time actually. Which means that when we solve this equation, let's assume we have here a domain like this, and we impose a source here in the middle, so a source, a point. When we solve the equation, we realize that this information will arrive in all directions at a speed equal to infinity. So it's going to be infinitely fast how this information arrive to these different locations in the domain. Okay, so the propagation of information is infinity, the speed of propagation, and all points are affected. So all points are connected. You do a disturbance in this flow, all points will feel it instantaneously, because in here this equation does not depend on time. Okay, so this equation is the one we will actually study most of the time in the course, and it's now interesting to see if we need to impose the boundary conditions. So okay, not only for this case but also for the cases of the parabolic and the hyperbolic equations. Which are actually these equations? Before talking about the boundary conditions, just allow me to remind you about the different kind of boundaries we can have. We can have inlets, outlets, and walls. And an easy way of defining this type of boundaries is by defining the sign of the product between the fluxes and the normal vector that is pointing outwards, as we just discussed in some slides before. So if the inlet, so we know that the inlet flux will point inwards, and the corresponding dot product with respect to this normal vector will be actually negative. And this is what defines an inlet. the outlet is going to be the opposite. So since the flux is pointing outwards all the time, the dot product of this flux with respect to the normal vector is going to be positive. And the last one is with the wall. When you actually have a flux, you may have a flux, but the flux is indeed just going, let's say, tangential. Therefore, okay, this is supposed to be a 90 degrees. So in this case, the projection is going to be 0. And this is what defines the wall. So we don't have flux coming in, we don't have flux coming out, and so on. Okay, now let's talk about the boundaries. There are 3 types of boundaries. We have the Dirichlet boundary condition, the Neumann boundary condition, and the Robin boundary condition. Depending on the kind of information we have for the problem, we will be able to apply either of these 3. For example, imagine you have, let me just put here a little drawing. Imagine you have a fin for a given heat exchanger, and because of experience you know that the temperature at this wall is going to be, let's say, 100 degrees Celsius. Because you know that, and now we are talking about temperature, then you will be able to impose at this boundary a fixed temperature which is going to be 100 degrees Celsius. So this is Dirichlet boundary condition. Now, sometimes you don't know this, that you have actually 100 Celsius, but you will know maybe that you will have a given flux coming from this wall. I'm talking about this wall just as an example. This is the same for all walls. Then in that case we will not consider the given value of temperatures, but we consider the flux. Okay, so in this case, let me just show you the next slide. So in this case we are talking about the flux of heat, and this is going to be given by the Neumann boundary condition. This is going to be used for us also for imposing adiabatic boundary conditions when you have this flux being 0, or also is very useful when you impose symmetric boundary conditions. Okay, and finally we have the Robin boundary condition, which is nothing but the combination of Dirichlet and Neumann. So we see here like a sort of Dirichlet, Neumann, like as a combination of the two, a sum of the two. We will see in the next class, when talking about finite differences, that this is very, let's say, of help. This is much of help for conjugate heat transfer. When you want to impose the flux that is going through a solid and equate this flux to the flux that is going to the, let's say, adjacent surrounding air. When you equate these fluxes, this is going to be the boundary condition you want to impose. You can call it conjugate heat transfer, and then you impose a Robin boundary condition. Well, and we arrive now to the exercises. This is something we will discuss when we meet in the MS Teams this Friday. But I want to give you an overview of what is waiting for you. Is you will discretize, you will solve analytically these 3 equations: a convective equation, a diffusive equation, and a convective diffusive equation. So the idea is that we will start working with MATLAB, getting familiar or remembering if you haven't used MATLAB in some time, and I will give you some Fourier analysis or in order to solve the corresponding equations in an analytical way, but you have to code a lot. We will just go to the discretization of the equations by means of finite differences and afterwards finite volumes. We will go through them in the next classes. So this time is gonna be more analytically. Okay, so we're up to the last slide. Thank you very much for your attention. We will talk anyway how we will communicate with each other during the course or during the entire course, actually, not only during the sessions but during the course. And I will also discuss with you what I expect from your work in terms of quality and in terms of projects. We will actually have projects at the end, and these projects are super important for a successful accomplishment of your work. And this is basically how I measure your enthusiasm, motivation, and also what you have learned during the course. Well, we will discuss this anyway when we meet in MS Teams. Okay, so bye bye.